going to be a review of Unit 4 of AP Chemistry. Just trying to get these out every week, but now let's stop labeling them by weeks and start labeling them by units. So yeah, again, this video is a review for Unit 4 of AP Chemistry, which is about chemical reactions. So we're going to go through and hit all those major topics. Not as many sample questions this time, but still lots of good review of the concepts. If there's anything in this video where you're like, dang, I wish I knew more about, well, let's not say titrations, but titrations or combustion reactions or particle diagrams, just let me know and I'd be more than happy to make this more specialized video on that individual topic. All right, so for today, we're going to be looking at chemical reactions. Again, it's about even distribution on the AP exam weighting compared to all the other topics. It's all about there, except for, I guess, intermolecular forces, which is a little bit more, and acid and base chemistry, which is a little bit more. But these concepts are going to be essential throughout the entire course. So I thought I'd highlight 5 things that students either struggle with the most or are skills that are just essential to doing good, doing well on questions related to this topic. The first one is, of course, writing and balancing equations. That is going to be essential throughout the entire course, even though it's not like the old test where there was an entire equation writing section. This is still an absolutely essential skill for succeeding in the course and on the test. Another thing students struggle with is using stoichiometric ratios in various contexts, whether that is in a chemical reaction and trying to predict the amount or calculate the amount of products or reactants that were consumed, or also in situations involving equilibrium. You have to look at stoichiometric ratios. In kinetics, you have to look at stoichiometric ratios. In gases, you have to look at stoichiometric ratios. In solutions, you have to look at stoichiometric ratios. So that's another place students struggle. Justifying why they identified a reaction type. Students can be really good at saying, oh, that's acid and base. Well, why? That's redox. Well, why? How did you know? How can you justify that identification? Many students struggle with that. So limiting reactant determination, super important. It's not like it's just going to be like that one hard question when it comes to AP Chem. No, like every question could potentially have a limiting reactant. Most of the FRQs are going to have that. So that shouldn't be like a challenge skill that you kind of ignored. That should be an essential skill. And then dimensional analysis in general. Being a pro at dimensional analysis in terms of like unit conversion at the beginning of the year is the reason why you start at the beginning of the year with that, with hopefully most teachers, is that you're going to need it desperately when it comes time for stoichiometry. So let's get rolling and go to our first topic. So according to their outline, introduction for reactions. The big thing here is physical versus chemical change. So remember, for a physical change, that is something that it could change the properties. That could happen. It's not going to change the composition. Okay, so that means that if it's H2O, it's still H2O. So some really common examples of physical phase changes would be like, physical changes or physical processes are going to be things that involve maybe a phase change, maybe bending or breaking or destroying something. Grinding something into a powder is a physical change compared to a chemical change. Chemical change is going to be defined by an actual change in composition, typically coupled with breaking and creating bonds. What are some of the signs of a physical and chemical change? That's what they really want you to know here. What are the macroscopic visual cues you can use to know a physical or chemical change has occurred? So a physical change is going to undergo some kind of change in properties or composition. This could be, like we said before, breaking something, grinding something up, ripping something up, melting, boiling, whereas a chemical change is going to have a new substance being formed. Oh, that's what I wanted to say. Another example of physical changes could be like separating a mixture. So when you use any of those separation techniques, that's usually going to be a physical change we're looking at. So chromatography, distillation, filtration, those are all physical. Chemical change, we're looking for things like a formation of a gas, some light or heat being emitted, which would represent a change in energy, a complete color change, or just we can tell we have a different product now. a precipitate forming. Those are all possible evidences of chemical change. So there we go with that. Moving forward, next topic is net ionic equations. So ionic equations, again, this used to be an entire question on the FRQ. They kind of toned it down a bit, but you still need to know how to write net ionic equations, what they mean, and why they're useful. So you should be able to take a reaction that's double displacement, which is what net ionic equations are usually going to be found in, and be able to compose a molecular formula, an ionic formula, and a net ionic formula from that. So some of the concepts necessary to really be able to do this is going to be a good handle on what's soluble and what's not, at least within the confines of the AP exam. And also understanding the composition of ionic compounds so you can write down how many ions are going to be formed. So we're going to use this as an example to kind of walk you all the way through it. This is going to start with a word equation, and we're going to turn that into a molecular equation and eventually into an ionic equation. So we have a reaction of aqueous sodium bicarbonate. Okay, so that's going to be NaCO3. And I know that this is a 2 minus here, and that's a +1. So we do our little swap and drop thing, and that becomes a 2 on the sodium. And let's keep going. And then we're mixing it with aqueous barium nitrate. So barium has a 2+ charge, and nitrate ion, hopefully you know your polyatomic ions by now, it has a -1 charge. So again, that little swap and drop thing, and you end up with a 2 down here, so that way that the ionic compound is balanced. They also told us that these are both aqueous. So it can be very, very helpful to take note of those when writing net ionic equations. And then this looks like a double displacement reaction. So essentially we're going to see the anions and the cations trading partners. So we have NaNO3 and barium carbonate. Now, they don't tell us if these are aqueous or solid. For some, we should know though. So you don't have to memorize all the solubility rules like the AP test used to kind of expect. Now, the only ones they expect you to know are soluble for sure are the following: Na plus, NH4 plus, NO3 minus, and K plus. How I help myself remember that, I imagine someone's asking me to go somewhere and I'm kind of annoyed and don't want to go, but I eventually give in. So they're like, hey, you want to go to the movies? I'm like, nah. You want to go to the movies? Nah. You want to go to the movies? No. You want to go to the movies? Okay, fine, I'll go. It's okay. So that's my little mnemonic to remember it. Come up with whatever you need. Those are the only 4 you have to memorize, are always going to dissociate, which means that they're definitely not going to be solid. In water, they're going to remain in the aqueous form. Now, barium carbonate, you're like, well, isn't there some solubility rules, something this or that? So for this question, it's not in these 4, which means on the AP exam, they either wouldn't give you that and expect you to know the solubility, or they would tell you. Like I've seen a lot where they give you the equation and then they want you to derive the net ionic equation. So if something's a solid, we're not going to break it down into ions into our next step. Before we can move on though, we need to balance this equation. I'll go over it right now. So when I personally balance equations, I've noticed that it helps to have a system. So the system I like to use for regular equations is MINO, and this stands for metals, non-metals, oxygen, and hydrogen. And I've noticed that when another teacher taught this to me, when you balance it in this order, you tend to be able to kind of knock all the balancing out in one go. It doesn't always work. Sometimes you got to go through it a few times. You gotta double things, and there's all these other little steps. But the most important thing is having an actual system when you're balancing equations. If you're just like jumping in at a random spot and I start just like focusing on balancing these oxygens and the nitrate, I'm going to have a bad time. It's going to take a while to get everything done. So just have some system. I like this MINO system. There is an addendum to the MINO system, which is if you're doing a combustion reaction, you want to balance it in this order. It makes it much easier to balance the hydrogen before the oxygen in a combustion reaction. Okay, so I'm going to go ahead and erase this so we can get started. So let's balance our metals first. I noticed that I have 2 sodium here and I only have 1 here, so I'm going to put place a 2 here. And then I'm going to balance my barium. I see I have 1 atom of barium and 1 atom of barium. Okay, so I'm all good with the metals. Next up are my polyatomic ions. I see 1 carbonate and 1 carbonate. I'm all good there. I see 2 nitrates and I see 2 nitrates. So I'm all good there. And hey, that's it. I don't rebalance oxygen. It was balanced in the ions. As long as those ions aren't breaking up, which is going to be most of the time, unless it's, say, a redox reaction, it helps that way. And then you don't end up with those weird oxygen ions that become a super pain in the butt to balance and becomes a little bit overwhelming. So keep the ions, balance them separately. Do metals, do ions, non-metals, oxygen, hydrogen last. It usually works out in your favor. Okay, so there we go. We have our balanced equation. Everything looks good. So we've got our complete equation. Now let's write our ionic equation. So for an ionic equation, you look at each compound and you ask yourself, what would it break up into? So sometimes this can help visually. So for sodium, let's make it the purple dots and let's let carbonate be the green dot. So we can see when this breaks down, it's going to form 2 purple dots. So that's 2 Na plus ions. I know that it's plus. Well, that's the typical ion sodium makes. Also, carbonate's a -2, so it balances out with that. And then I'm going to have the carbonate ion. All right, next up, I have barium. So again, I can think of this as sort of graphically, if that helps you. So barium will be red and the nitrate will be black. So I see I have 1 barium and NO3, 2, so 2 nitrates. So I'm going to have 1 barium ion and 2 nitrate ions. Oops, gotta put that 2 there. All right. And that is our first part of the reaction. And now on the other side, we're going to write the rest of the ions out. So now we have 2 NaNO3. So this means NaNO3 would be purple for Na. Try to color code this. And black for nitrate. And we have 2 of them, though. So make sure that you pay attention to the stoichiometric ratios as well when you're writing these ionic equations. And we're going to ask ourselves, what is this going to break down into? Well, it's going to break down into 2 Na pluses, and it's going to break down into 2 NO3 minus. All right, we're going to keep going. And then we have our barium carbonate, which is a solid, so it's not going to break down into anything. It's going to stay solid. It's not going to dissociate into its ions. All right, so this would be our complete ionic equation. And finally, we're going to go through and we're going to cross some stuff out that's the same on both sides. So I see I have a sodium here and a sodium here. So these are what we call spectators. Spectator ions. They're just watching the show. They're not really doing anything. And we also have that the case with the nitrate. So we're going to remove them from the final equation. Now the word net, what does it mean? So you can imagine it's what's left over. You're catching it in a net. Net in general just means like the final balance once you kind of cancel things out. So that's like the end of the amount of money you make at the end of the year after all your expenses is like your net income as opposed to your gross income. Okay, so CO3, 2 minus, plus the barium ion, and that's going to become BaCO3. So that's the real chemical reaction that's occurring in this particular reaction. Even though there was sodium and nitrate involved, they were basically being spectators. They were not really active in this process. So a lot of times, scientists or chemists in the actual lab setting, if they want to combine barium and carbonate, they have to find a way to get it in there. You're not just going to find a pack full of carbonate ions. They're going to be bound up with some other cation. So they'll use something that's highly soluble like sodium or nitrate to help deliver these ions to solution. So these 4, especially when you see these 4, they're usually your spectator ions. There can be other spectator ions as well. But these ones are the ones you need to know are always going to dissociate. So they are the most common ones that come up for net ionic equations. All right. If everything was aqueous here, if for some reason this was AQ, we would say that there would be no reaction. Everything just sort of dissolves and undissolves back and forth forever. It's just at this equilibrium. So just be aware of that. If something is a solid, in the reactants, it's not going to be able to dissociate. So, I mean, not that if it's a solid, but if it's a solid that's not soluble, it's not going to break down. So you're not going to have your double displacement. So double displacement is dependent on whether the reaction is soluble or not. Okay, moving forward, representations of reactions. Okay, so this topic, representations of reactions, is really essentially all about particle diagrams. AP loves particle diagrams. They kind of always like them, but especially the past few years, they love to see if you can connect this microscopic worldview with the macroscopic world of chemistry as well. So we can actually take these diagrams aren't just for fun. They're not just drawing some random dots to make a picture to help you understand. The particle diagrams on the AP exam are designed the way they are for a specific reason. These actually represent the number of moles or molecules present in the correct proportion. So we can actually look at a particle diagram and derive a chemical equation for it. So I'm gonna make a little key right here. And this is pretty common in chemistry, but sometimes they use different colors, so be careful. So I'm gonna call the red one oxygen and the white one hydrogen. And where I see things are stuck together like this, that means that's a chemical bond. So I have some H2, and looks like I also have some O2. And this reaction is going to go ahead and turn into H2O. Now I can literally count how many I have. I have 8 H2s, and I have 4 O2s, and I have 8 H2Os. So this equation would represent this diagram. You could also reduce that equation and it would still be a good representation of this diagram. But I think most of you hopefully can connect these images with the equation. Again, be careful. The actual numbers of things matter. You can literally count them up and match them up. It's not like just, oh, there's some H2 and some O2. No, this is telling you the ratios. So something AP likes to do the most is they put in a little bit extra something. Okay, so, and they'll often say like, what's missing, draw it in, all kinds of stuff. So if this was the case, those oxygens are in excess. We already counted up 8 oxygens and 16 hydrogens to make our H2O. So these two are gonna just be extra. And maybe you had like, I don't know, some weird catalyst in the corner that's helping this reaction occur. You still see that catalyst there as well. So same thing with the net ionic equations. You might have these spectator ions. They're not even doing anything. They're just floating around. If they were asked you to draw a particle diagram with net ionic or with spectator ions, you best believe you're going to see it. Same thing if they give you a diagram, say about dissolution, that you should expect to see the spectators as well. So final word on particle diagrams, realize that these aren't just random drawings. The numbers actually matter and they represent something. Be able to go back and forth between particle diagrams and equations. They are equally valid in representing it. Not necessarily the most commonly used when you're trying to do calculations to draw an entire particle diagram, but it is something that AP tests very frequently. Okay, physical and chemical changes, we're back here. So they have physical and chemical changes in the outline of the unit twice, and that's because in this case, they want you to focus more on bond interactions. So what they want you to know in terms of physical and chemical changes we'll look at chemical ones first. So chemical changes usually, well, not usually, I guess always, creating and breaking chemical bonds. So we end up with new chemical species when we have chemical changes because bonds are literally created and broken. For physical changes, it's usually just IMFs. So be very careful of focusing on the difference between chemical bonds. These are actual covalent and ionic bonds, and intermolecular forces like hydrogen bonding or London dispersion forces. That would account for why a phase change occurs, or that would account for how you might be able to separate two materials based on IMFs. Now, sometimes a physical change can have chemical bonds breaking. And you're like, wait, that's blasphemy. What are you talking about? And this is like probably one of the hotly debated topics in this section, which is the dissolution of ionic solids. So when you dissolve something in water, you technically are breaking those ionic bonds. So bonds are being broken. But then again, you might say, well, nothing really new was created. It's just that the sodium and chlorine dissociated. So I feel like there's arguments when it comes to dissociation dissolving for both the physical and chemical changes that are occurring. So just be aware of that. Chemical changes is always going to involve creating and breaking bonds. Physical processes or interactions that are working with IMFs are usually going to be considered, well, physical. All right. Moving on to everyone's favorite topic. At this point, stoichiometry should actually be a bit of a relief. I'm hoping if you've really been studying for the AP exam, this should be, I'm hoping, one of the easier things for you. If not, that's okay. There's still time to practice, but whew. All right, so underlying the whole idea of stoichiometry is the conservation of matter. So the mass of your reactants should be equal to the mass of your products. Now, sometimes you might be like, well, I don't have that. Well, think about it. If you burn something, for example, CO2 is escaping into the atmosphere, so is water. So if you don't have a controlled vessel, if you have it open to air and gas is being produced, yeah, that gas can be some of the mass that's missing. Or if it's reacting with your reaction vessel or all kinds of things, there's always a reason why the mass is not the same if the reactants and products have a different mass. It went somewhere. It didn't just disappear. So remember that for chemical reactions, at least. Let's not get into anything nuclear. So that's underlying the whole thing of stoichiometry is the mass of reactants and the mass of products is the same. Now, there's also this concept called the mole. And the mole is based on Avogadro's number, right? And that equals 1 mole. And the reason why this is important is because between the periodic table with the little atomic mass values and the mole, we can actually use, there is a conversion factor there of that's how many. So let's say you had carbon has a molar mass or has an atomic mass of 12. Then 1 mole of carbon has a molar mass of 12 grams. So to convert from AMUs, which is the small atomic mass unit, to grams, we use the mole value, or Avogadro's number, as the conversion factor. The reason why this is important is because when we look at our chemical equations on maybe some of these past ones like this, it said nothing about mass. It's literally talking about the number of molecules that have to react. 8 molecules of hydrogen and 4 molecules of oxygen make 8 molecules of water. Okay, doesn't say anything about their mass. Yeah, the mass is going to be the same, but hydrogen and oxygen atoms don't have the same mass. So using mass in chemical equations is usually not our best bet. We typically want to use moles because moles is a counting unit and it actually allows us to compare the ratios represented in that equation. So the mole is sort of like essential to the entire concept of stoichiometry. It allows us to take other quantities that aren't necessarily counting quantities, things like mass, things like, I guess you could even, in some cases, like volume and things, that's going to be dependent on other factors like density and whatnot. And we can basically compare them using the concept of the mole. So if you don't know what the mole is by now, a couple weeks before the exam, bless your heart, maybe just take the test next year. Okay, here's a little roadmap that helps you connect all the ideas. So if you are struggling with stoichiometry a little bit still at this point, you're like, I get it sometimes, I don't at other times, using a little map like this at first can be really helpful. So let's say we had the mass of something reacting and we wanted to know the mass of another product. Well, we can convert our mass to moles and using the molar mass, and then we can convert moles to moles using the stoichiometric factor, which is based on the balanced equation. And then now we'll have moles of B, and we can use that to convert to mass of B. You can use any of these different starting points, and it tells you on this one at least what allows you to convert to the next box, and then you can find where you're at. If you can notice, at the heart of all of this is moles. So sort of when in doubt, when trying to do some kind of calculation, try converting to moles and see if it's going to help. It's definitely going to help for a lot of chemical reactions. Not everything in the course, like thermochemistry, it's not always moles you want, but definitely for chemical reactions. Okay, which takes us to the last thing that we want to talk about in stoichiometry. Now, I could practice stoichiometry with you for hours, but there's awesome videos online. Tyler DeWitt's one of my favorite. So check him out if you are having trouble with stoichiometry. He does a good job of explaining it. There's lots of resources. The last thing is limiting reactant. So I'm going to explain the concept real quick. And I always like using sandwiches as an example of a chemical equation, right? So in this one, we have a stoichiometric ratio where it's 2 slices of bread plus 1 slice of cheese. So we see here that if we have 28 slices of bread, but only 11 slices of cheese, since every sandwich needs at least 1 slice, we only can make 11 sandwiches. The rest are going to be left over. So one of these is limiting, and that would be the cheese. And the excess reactant would be the bread. Same thing in a chemical reaction. We want to think about how many, not grams we have, but how many moles. So limiting reactant, always use moles. And we want to see which one we have less moles of proportionately. Now in this case, yeah, we had less cheese. We only had 11 cheeses. So you could say, oh, that's the limiting reactant. But what if we had 20 cheeses instead? Well, 20 is still less than 28. So you can't just say, oh, it's less because there's less slices, because in this case, since you need 2 slices of bread, it's not going to work. You need to compare the mole ratios between the two. So first you have to convert to moles, and then you need to consider the mole ratio between them. Assume there's going to be a limiting reactant. If they do not say excess, if they don't tell you anything, but if they give you 2 molarities and volumes or 2 masses, there is a limiting reactant. Most of the time on AP chemistry questions, there is a limiting reactant. So make sure that you account for that when you're looking at any kind of problem related to that. Okay, and again, if you have trouble with limiting reactant problems, I'm not going to do a whole example. There's tons of videos online, but if you do want me to give you an example, I'd be more than happy to walk you through it. So, yeah. Okay, next topic is introduction to titration. Now, a lot of teachers don't teach this early in the year. They just say, oh, we'll save it all for acid and base, the acid and base unit. The problem with the acid and base unit is you get so overwhelmed with all these definitions and weak acids and buffers that a lot of times the basic concepts of acids and bases get lost, which are essential to understand titration. So in a titration, first of all, you should know sort of like how this thing's set up. Hopefully everyone got to do it in class. If for some reason you only did a digital titration or something, that's okay, as long as you remember what stuff is. So this is called the burette. That's what's delivering the fluid down into the flask. We try to use a flask instead of a beaker because it's more like less splashing is going on. A burette's unique because the numbers go the opposite way as you fill it up. So just be aware of that. Let's see, what else? Yeah, so the numbers will be the smallest up here and the biggest up here to basically help you see how much you added. The titrant is what you know and you're adding in the titration. The analyte is the thing that you're analyzing it. There's usually an indicator. It doesn't always have to be pink. Let's see, what else? I think that's the main things you need to know. Oh, okay. So when you rinse out a burette before you add your titrant, you want to rinse it out with a dilute version of that the titrant that you're using. You don't want to use water. It will dilute the titrant. You don't want to use tap water. It might have ions in it that could precipitate with the titrant. The main idea so that's the setup and the vocab you should know. Be aware of that. They do love asking those little lab questions. that you need to know the equipment and the setup as well as the chemistry. The concept here, though, is that you're adding a known amount of moles of acid. Now, you usually don't know, it doesn't say the moles, it tells you usually the milliliters, or you could basically think of that as liters. So you're going to multiply the liters times the molarity, and it will actually tell you the number of moles you added. Then when you have a chemical equation and you know how many moles you added of one thing, you can figure out how many moles you produced of something else. So that's the essential idea here, is that you are adding a certain number of moles and you're watching for a certain type of reaction. Now, typically a titration involves acids and bases where you're trying to find an equivalence point. That is going to be the point where the moles of, at least for if it's a 1-to-1 ratio, it's going to be the moles of titrant is equal to the moles of analyte. That's going to be at the equivalent point. It can get a little bit more complicated if it's not a 1-to-1 ratio, but for the sake of the AP exam, it's going to be a 1-to-1 ratio. So the moles of titrant equals the moles of analyte that were reacted. Typically, you kind of know where the equivalence point is going to be beforehand. We'll get more into that when we get to advanced titrations in the acid and base unit, but you have an indicator that lets you know when the pH has been hit. So as this process is happening in an acid-base reaction, at the equivalence point, your pH is going to change pretty rapidly as it goes through that point, because the dominant species in that solution is changing. So in a titration curve, you take data points of how much volume you added and what the pH was at these different points, and you find the equivalence point. So for a strong acid, strong base titration, the equivalence point is going to be at 7, but we're going to see later for other kinds of titrations it's not, and you continue to plot these points. Now, pH scale is a logarithmic scale. Each time it goes up by 1 on the pH scale, it's actually going up by 10. 10 to the 1, 10 to the 2, 10 to the 3. Well, it's actually in the opposite direction, but it's still a scale of 10. So that's why you see these rapid shifts happening. And why they don't keep going is because this is actually a logarithmic scale, which means that each time the y goes up by 1 value, it's really going up by a factor of 10. 1,000, 100, 10, etc. Okay, I think that's kind of it for titrations. Again, this is just an overview of the basics so that when you get to acids and base unit, you'll know what's going on. All right, types of chemical reactions. So these are some of the basic types you should be familiar with. Of course, a combination or synthesis reaction is when two things come together. Decomposition is where it's breaking down. Single replacement. Okay, so this is the one where I feel like this is how I think of it. I imagine B and C as a sweet couple, and then A is just like Lexi and just is like, bam, get out of here. And C is kind of unloyal, I guess. And now you got this new loving couple, the AC, and the B has been displaced. So that's a single displacement reaction. There's also double displacement reaction. That's like a swingers party or something. That's where they're switching partners, right? So B is now going to switch with D and D is going to switch with B. You end up with these two new compounds. This usually happens in solution. It's essentially the main form we're going to look at for acid and base reactions, as well as most like precipitation solubility style reactions. And then there's combustion. Combustion is always going to feature some type of hydrocarbon. This could be a hydrocarbon with more than just C and H. Sometimes they throw in O. I've even seen AP questions where there's N in the hydrocarbon, but it's going to be combined with oxygen. So let's forget the N for now. And it's going to produce CO2 and H2O and heat. It's always exothermic. Okay, so that's your combustion reaction. Let's see. So you might be, wait, when I burn stuff, it makes a lot more than CO2 and H2O. Well, this would be a perfect clean burning system, would only produce those products. Now, any other impurities in your hydrocarbon or in the combustion system that's burning it could produce the heat maybe could react with other things as well, could produce other essentially like smoke and stuff like that. Okay, there's a couple more that were worth mentioning. So combustion they can be tricky to balance sometimes. Again, I really recommend using the CHO method, which is balancing carbon, hydrogen, and then oxygen. It makes it a bit easier because there's an odd number of oxygen on this side and usually an even number on this side. It's sometimes challenging to do that. The other place is if you get stuck is double everything. on a combustion reaction. Just multiply everything by 2. A lot of students get stuck because like there's an odd number here and an even number here. Every time I increase this one, I have to increase that one, and I'm going around in circles forever. If you get stuck like that on a combustion, double all your coefficients and then solve it, and hopefully it works out. And then you can always reduce them down if for some reason the numbers are too big, right? You always want your equation to be in simplest, most simplified coefficients. Okay, so those are the types of chemical reactions you should know a little bit more. Acid and base, there's different definitions of acid and base, so use that term loosely. Usually acid and base is going to have something, not always, something that can donate hydrogen and something that can receive hydrogen. So this would be like an acid and base reaction, and an acid-base reaction, at least in aqueous solution, is going to usually produce water and HCl. There are acid and base reactions that are not in aqueous solution, but it's not in the scope of the AP exam, so don't stress about it. Finally, a redox reaction. So how it defines a redox reaction is that there's a change in the oxidation numbers. We'll get to redox in a minute. Change in oxidation numbers, which essentially means that there is some kind of change in the charge, the amount of electrons with different elements in the reaction. This usually does not happen. So in redox, that's what's going to give it away, is that there's a change in oxidation numbers. Some atoms gained electrons, some atoms lost electrons. That's what defines redox. So at the very beginning, I said one of the things that students struggle with, let's go back and look at that slide real quick. Okay, the biggest weak points for students is writing and balancing equations, right? We touched on that. Using stoic ratios in various contexts. We started to look at that. This will keep popping up throughout the course though. Justify identification of reactant type. Okay, that's what we want to work on. So we need to be able to say why these things are what they are. You should be able to not just identify them, but explain why. So the replacements aren't too bad. There's obviously a greater affinity for one of the ions than the other. That's why they essentially replace. Combustion, you can bring up that it's oxygen burning and CO2 and H2O are being produced as a byproduct. Decomposition is obviously one thing turning into more than one. Combination is having more species and it becoming less. And then for redox, you're looking for that change in oxidation numbers. That's how you're going to define if that it's redox or not. Acid and base, you're going to use the acid and base definition. So that's going to be that one of them gave up a hydrogen and the other one received a hydrogen, since we're going to be mostly using the Bronsted-Lowry definitions for the rest of the course. Okay, real quick, this is the activity series. So activity series are in determining single replacement displacement, however you want to call it, single displacement reactions. So this essentially tells you who's, like I said, it's kind of like A came in here and was sexier and kicked B out. This is telling you like which is the most attractive or most reactive elements. So the ones at the top, potassium, sodium, lithium, you're seeing a little bit of a pattern. Our alkali metals, and then our alkaline earth metals are some of the most reactive substances. And that means that they are going to kick out another cation that is there, and they're going to be the ones making that ionic bond. You can break it down to ideas related to the attraction. There, you can get down to like an atomic view of it. Just know that in general, alkali metals are really reactive. And as you go down, alkaline is not as much. It gets sort of blurry, the reasons why. Not to say that there isn't a reason why, but it's a little bit harder to explain for this section, right? For the most of these transition metals. And then you start to see down at the bottom, metals that we often consider like precious or almost like noble metals: platinum, gold, silver, copper, mercury. These ones are very unreactive, so they tend not to displace other things. You don't need to memorize the activity series, but just be familiar with the general reactivity of metals. These pretty metals we all love are very unreactive. That's part of the reason why we love them. And the alkali and alkaline earth metals are very reactive. Okay, so quick intro to acid and base reactions. We do not use the Lewis definition in AP Chem because we're always looking at aqueous solutions. So you can eliminate that. And then Bronsted-Lowry is the main definition we use, although the Arrhenius definition is pretty good too. The only problem is it always talks about in terms of H plus and OH minus. There are actually some bases that aren't, oh, I guess they still add OH minus to solution, but they don't have an OH in them. So again, the Bronsted-Lowry definition is the main one that we focus on, although the Arrhenius one is useful as well. Notice here that there's this statement. Oh, I think we missed one on the last page. So also reducing agent, oxidizing agent for redox, that's just confusion. So that's not going to be on there. Also, it says right here, solubility rules are not going to be assessed on the AP exam. You just need to know your nah, nah, no, and K. All right, back to acid base. So again, it says Lewis base concepts not on the exam, so we're not even going to worry about it. We're going to use the Bronsted-Lowry definition. An acid is something that donates hydrogen, and a base is something that accepts hydrogen. So neutralization is probably the first thing we want to. Now, again, a lot of teachers don't mention acid base early in the year because they said, well, we'll get to it all later, which is great. But a lot of students miss out on this big concept, which is acid-base neutralization. When you combine an acid and a base, you get water and a salt. All right, that's all there is to it. And it's, you notice this is a solid arrow, not an equilibrium arrow. When you think about an acid-base neutralization, don't worry about equilibrium or weak acid, weak base yet. It's just a stoichiometric ratio. So you can calculate how much water and how much salt's going to be made. When we get our acid-base video, we'll worry about the rest later. But in general, you should be familiar with that. It's basically a double displacement reaction where you produce a salt, which is a salt is just going to be some ionic compound. That was the result. That was part of the acid and base, and you're going to get water. Basic neutralization reaction. You can write a chemical reaction and you can balance it out and you can figure out what you're going to get. The last concept that they mention is worth talking about here is water ionization. Now, water itself, not very much. The K value at standard 1.0 times 10 to the negative 14. So it doesn't really happen very much, but it does happen. Water itself can turn into ions of H3O plus and OH minus. This does occur sometimes. It much more heavily favors the reactant side based on that tiny K value, but this does occur. So water can act as both an acid and a base, and there is a very slight amount of ionization in water. So be aware of that. It's often written as KW. We'll talk more about it when we get to acids, bases, and equilibrium. Okay, final topic is redox reactions. Now, 100% sure, but I think from everything I've been reading from AP, they're not, you don't have to know how to balance acid and base in like acid. I mean, you don't have to know how to balance redox reactions in acids and bases, which is kind of a little bit of a harder process. I still teach it to students, but I don't think it's necessary. Don't quote me on that, but I'm seeing really mixed answers about that online. Although from what's official, I don't think they would make you balance redox in acid and base. Although it seems like every teacher online is teaching their students how to do it. So take that what you will. More important than being able to balance them in acid and base, even if that did come up, is being able to apply the oxidation numbers. This comes up not just in redox, but I've seen standalone questions that just talk about oxidation numbers. So there are some rules here. You can't get away from them. Elements. The oxidation number of an atom in its elemental form is 0. So in its naturally occurring form, whether that means a piece of iron, just Fe, or some oxygen, O2, the oxidation number here is 0. Oxidation number is essentially sort of a representation of how many electrons, the electrons that are around that atom. So monoatomic ions, so stuff like Na plus or Fe2 plus, the oxidation number is going to be that charge of that ion. So if there's any ion at all present, then the charge on the ion is going to be its oxidation number. Oxygen almost always has a oxidation number of -2. There's a couple exceptions. There's hydrogen peroxide where it has a 1, And there's also the compound with fluoride, F2O, where it has a oxidation number of 2. But almost always it's going to be -2. Hydrogen is almost always a +1. Halogens are usually always a -1, unless they're kind of following one of these other rules. Chlorine is always -1. The only reason chlorine or those others aren't is if oxygen or fluorine kind of are in the same compound and sort of trump it. And finally, compounds and ions, the total oxidation numbers of an entire compound or ion is equal to 0. So you can kind of use these rules that you know to kind of work backwards. So something like HClO4, and we want to know the oxidation number of all 3 of these. This one would be a +1. Oxygen would be a -2. And since the sum of this whole compound has to be 0, I have a total of -8 oxidation number coming from oxygen, since there's 4 of them, and +1 from my hydrogen, which means that chlorine has an oxidation number of +7. So that's how you kind of work backwards to figure out oxidation numbers. All right, the last concept with redox is half reactions. So this is a chemical reaction, and you might ask, they might ask you, is this a redox reaction? How would you know? Well, we would have to calculate the oxidation numbers. So oxygen's easy. It's going to be 2 on both of these. Magnesium is like in its elemental state, so it's going to be 0, and so is copper. And we have to remember that these compounds are going to be a net of 0. So that means that this copper must be +2 to balance that out, and this one has to be +2 as well. Okay. Then when we have a redox reaction, usually what we want to do is we want to break it down into 2 half reactions. So we're going to take what we were given. In this case, it's going to be CuO, and it's going to become Cu. And in this one down here, I have Mg becoming MgO. Now, before we get started, let's identify which one is the oxidation reaction and which one is the reduction reaction. So what I see is copper had a +2 and it went to 0. That means that it gained 2 electrons. Okay, so in my equation here, I'm going to write those 2 electrons in as well. So this is part of the half reaction process. You write in the electrons that are essentially going to be gained. So this copper gained 2 electrons and it became copper metal. In this case, and then we call this, so here's the mnemonic, Leo says Gur. So when you lose electrons, that's oxidation. Lose electron, oxidation. And when you gain electrons, that's reduction. Okay, so in this case, since we gained electrons, this would be our reduction reaction. And this one, it goes from 0 to +2. So this must have lost electrons. How else could you go up in charge if you didn't lose something negative? So when this is formed, those electrons are essentially released out into the world. Okay, we want to make sure that when we balance a redox reaction that we have both the same elements on both sides and the same charges, and we kind of have that. Now, sometimes this doesn't work out nicely. You might have 3 electrons or something. Then, and that's the case, you have to multiply everything by a coefficient so that the number of electrons that are being involved in the reduction and the number of electrons involved in the oxidation are the same. So the reaction can sort of cancel out. So the 2 things you have to do when working with reduction reactions is balance the atoms balance the charges. There's a whole process to go through when you have this happening in water. When there's acidic or basic solutions, you use water and hydrogen ions and OH ions to essentially balance out these equations. But again, as far as I'm reading, although it's on every review site, I don't see that it's on the AP exam. So I've made other videos about it in the past, so if you want help, I can definitely help you, but I don't think it's worth your time stressing about how to balance them in acid and base solutions, and just focus on the idea that it's about balancing the atoms, balancing the charges, being able to assign oxidation numbers, being able to determine reduction and oxidation reactions is going to be very helpful when you get to electrochemistry at the very end. So I think that's it. We tried to go through everything. Thought the video would be shorter, still ended up being pretty long. That's okay. If you liked the video, if it helpful, like and subscribe. If you didn't, let me know how it could be better. Again, I'm here to support whoever finds this video. So any way I can help you, whether that's practice tests, whether that's more videos, whether that's explanations, whether that's worksheets, let me know. I'd be more than happy to send some resources your way. If you're still watching, good luck on your AP exam coming up in a couple weeks. You got this. Don't give up now. Just keep studying and have a great night.